Looking over the questions that y'all had, the biggest one by far, the one that was most common, was quasi period and quasi frequency. So I thought we'd take a look at that. If you're comfortable at all with frequency and period, just regular, quasi frequency and period is really not any different with one slight exception. But if you already have those ideas, it will not be a big leap to see what's going on with quasi period. In fact, it is exactly the same idea. It's just a different name, essentially in the case when there's damping. You would talk about frequency and period when there is no damping, and then you just change the name to quasi frequency, quasi period when there is damping or non-zero damping. But the principles are the same, and we'll see how that works. But first, why don't we go ahead and look at what period and frequency are, or remind ourselves. I'm guessing for a lot of people this is understood already, but just as a reminder to set ourselves up for quasi frequency and quasi period. All right, so here I have written the period, frequency, and angular frequency. So the period, quite simply, is just how long it takes to go from one peak to the next. I'm going to draw a little diagram here as well. So all this is written out. But with period, what you're doing is you're looking at a sinusoidal curve. You know, it could be cosine, could be sine, could be both, but it's going to look like a sine curve shifted or a cosine curve shifted. And let's say that looks like this. Let's say it kind of goes like so. This is going to be really rough, but hopefully that gives the idea. Simply, the period is how long does it take to go from, let's say, this peak to this peak, or really any peak to any successive peak. So this length of time, this is the period. Usually that's measured in seconds, but it could in theory be in minutes or what have you. The frequency, on the other hand, is if you have a unit of time, let's say 1 second. So suppose, I don't want to do this. Let's say here. Suppose that this is 1 second, what I've drawn in yellow here. If what I've drawn in yellow is 1 second, we'd like to know how many cycles from where a cycle is going from peak to peak. How many do we go through? And if we look at this, it certainly seems like we do not go through we do not get through a full cycle in this amount of time. So the frequency in this little diagram that I've drawn, maybe the frequency is something like, I don't know, 0.75 or something. Maybe it's around 3/4 of a full cycle. We certainly don't get through a full one. And why not? Because we start up here and we travel through, and by the time we get to down here, we do not get back up to this level spot. So we don't make it through a full cycle. So maybe the frequency would be about 3/4 of a cycle every second. And there's an obvious relationship between the two. If the period is seconds, then you want to know how many cycles do you get through in a second. So the frequency is just 1 over the period, and vice versa. The period is 1 over the frequency. And actually, you could say this if it helps to see it this way. You could see it as something like seconds per cycle, if you like. Like how many seconds does it take to go through 1 cycle? I think that makes the relationship a little more clear, the reciprocal relationship. There's another term called angular frequency, and I've set these colors up here and here cycles versus radians to maybe make it a little easier to remember what the relationship is. If the frequency is the number of cycles per second, or the number of times the peak is reached per unit time, excuse me, going from peak to peak is the same as running through 2 pi radians. So instead of going from a peak to a peak, it's essentially the number of radians you run through. And going from a peak to peak is 2 pi radians. So when we look at the angular frequency, we're saying instead of measuring number of cycles we get through, we're going to, for each cycle, we're going to go through 2 pi radians. So one way to look at this, alternatively, if it's radians per second, in terms of unit analysis, actually, let me put it under here. There's 2 pi radians per cycle, and the frequency is 1 cycle, or I should say f cycles per second. And then we can see that that gives us the 2 pi times, I'm trying to get this one, there we go, 2 pi times f. And then that, through unit analysis, gives us radians per second. So this is just the base period and frequency. And now I want to highlight here and say all this stems from the case of no damping. So let me really put enlarge on here. So this is when there's no damping. And I'm pointing that out because the pseudo frequency, pseudo period, et cetera, comes in when there is damping. So this is the case when there's no damping. When you want to look at the pseudo period and pseudo frequency, like I said, that's when there's damping. So now let's suppose we want to find the pseudo period / pseudo frequency. If you find either one, you get both because they're related reciprocally. So let's look. Suppose we have a system and we have a mass of 10 kilograms. We have a damping constant of 2 kilograms a second. And then we have a spring constant of 1 kilogram per second. And just as a reminder of what these things are, because I'm a firm believer that reviewing is always a good thing. So it's mass, this is damping constant, or maybe actually damping coefficient might be the more formal term. And then finally, spring constant. All righty. Sorry, I did just something on the computer. So what do we do in this case? What we'd like to do is find out the, well, first let's write the differential equation, the model for the spring mass system. The model for this system, it's going to be a differential equation. That differential equation will be, in general, mx double prime, mass times acceleration, plus c times x, the damping times the velocity. The faster you go, the more there's resistance. Think of air resistance. The faster you go, the more there's fluid resistance against your movement. And then kx. In this case, we won't be driving the force. There's no forces besides the natural ones, so we'll just set it equal to 0. In particular, this gives us 10x double prime plus 2x prime plus x. You may be wondering, why did I write mx double prime and so on? One reason I like to do that is just to continually reinforce what the model is so that I don't have to think very hard later. The more you can reinforce fundamentals so they're second nature, it just frees up your brain to deal with other things. And you don't have to try to remember, how does that model work and so on. That's why I like to reinforce fundamentals a lot. Frees up brain power. So we have this thing. Now what we want to do is find the characteristic polynomial. That polynomial is P of R is equal to 10R squared plus 2R plus 1. The roots of that polynomial are going to be R is equal to negative 2 over 20 plus or minus 1 over 20, and then 4 minus 40, which gives us negative 1/10 plus or minus 6 over 20I, which is negative 1/10 plus or minus 3/10 I. So this I got just from using the quadratic formula. Our solution then is going to look like this. It's going to be x is equal to C1, first parameter, e to the negative 1/10 times t times cosine of 3/10 times t. And the second term will be very similar, except that there we will have a sine. Now I'm going to take this and I'm going to put it on another page so that we can put some graphical representations. But if you want to come back to this page I was just on, let me know and I'm happy to do it. But this process is something that's similar to what we've seen before. Finding the characteristic and then characteristic polynomial, finding the roots, and then finding the solution from that. Now what I'm going to do is I'm going to approximately graph this. And what this will look like is we have an x-axis, we have a t-axis. Maybe I will color x. How about cyan? And then I want to use this color magenta here to show that there's going to be some kind of damping envelope. It might look something, I need to do it dark enough that you can see, but light enough so that it's not too distracting. So maybe it kind of looks something like this. It's this exponentially decaying envelope. And it's supposed to match these two colors here and here. It's this term, or this factor, I should say, in each term that causes the damping, because this number is going to get smaller and smaller. Cosine and sine will just oscillate between 1 and -1, but this pushes the amplitude down. And in particular, excuse me, because it's a negative, it's negative 1/10. So it's like 1 over e to an increasingly large exponent. Now with cyan, what I'm going to do is I'm going to start up here and show that we have this oscillation like so. Now, quite simply, if we want to find the quasi period, it's just the time from one peak to the next. So I say peak, meaning that the peak, we don't have exactly a notion of amplitude in the sense that it always reaches a certain height, but we do have a notion of a peak in terms of, if you think about like a local maximum from Calc 1, I think it would have been. And just in the intuitive sense, when I say peak, I'm sure there's something that you kind of imagine, and that is, maybe let me put it in another color. That is, here's a peak, and then here's a peak. And quite simply, we want to look at, well, how long does it take to get from one to the next? This time is the quasi period. And it's going to be the same between every pair of peaks. So though I may have drawn it with some additional space, though they may look different, they would be the same. So it's just a matter of, me not being a computer, so not drawing it perfectly spaced. But this is the quasi period, and it should always be the same, even if it graphically looks a little different now. The big question would be now, well, how do you actually compute that? We can graphically see what's going on. I don't think that's very hard. It's just peak to peak. But how do you algebraically compute this thing? Well, that's actually not very hard either. When you imagine the following thing, if you think about how to get, let's take the first in particular, to go from here to here, that would compute the quasi period. That's a matter of going from t equals something to t equals something else. The first thing, and maybe that seems like a simple statement, but that's to kind of reinforce that this is a simple computation once that's clear. What you're doing is you're going from t equals 0 to t equals something. Maybe I'll call it TP for the period time. Now, what that, how do I want to say this? And actually, we start out at C1 here. Let's see. How do I want to say this? Yes. When you have regular cosine, let's say, if you have cosine of t, and just to make sure that you're following along, that I'm not sort of talking and it's not clear what I'm saying, what I'd like you to do in chat is to say what you think. For cosine, it starts out at 1, it dips down, and then it comes back to 1 at some point. What is the point at which it gets back to 1? So you're at t equals 0, and maybe if this was x, then it takes some amount of time to get back to 1. So t is equal to 0. What's that amount of time? Or what do you think? Again, I'm not like judging whether you're right or not. I'm just trying to get a sense of where you are. And if you're not sure, you can just tell me, and that lets me know that you're not sure, and I can then explain more. There's no bad answer, even if it's not the correct thing. It just tells me where you're at, so I can help you out. I see a few, and maybe we'll let a few more answers. Okay, that looks like a good chunk of answers. So thank you to everyone who gave answers. Now, cosine and sine, just regular cosine, regular sine, they both go through a full cycle over a time, or over a number of radians equal to 2 pi. If that's not clear when we sort of stretch it out like that, think of the angle it takes to go from here around back to here. That takes 2 pi radians. So too does it take here 2 pi. And you can think of it in terms of radians, but that'll work for t as well, since t is the thing that's here. Now, if it takes 2 pi to go from peak to peak here, what's going to change if we take that cosine of t And instead of having cosine of t, we multiply cosine of t by some coefficient function. Let's say e to the negative t, cosine of t. Say our x is now that. Well, because of that e to the negative t, and maybe I'll just keep it the same color. Because of that e to the negative t, we're now damping. But if you think about what happens with cosine, it's still going to take the same amount of time to go from the peak to peak, because that peak is decided by cosine. So though the height will change because of this coefficient, the time it takes to go from max to max does not change. So therefore, it's the same period, and it's decided by what's in here. At the same time, so that damping coefficient is not going to matter. We only care about what's going on with cosine. Now, with that said, I'm going to move this to the next page. And again, I'm going to ask you a question, and I'm curious what you think, and I am looking for and appreciate answers. Let's say we now have x is equal to cosine of 4t. So it's different now. It's cosine of 4t. How long, and you can think of this in a few ways, how long is it going to take for this thing, which I won't draw because I don't want to give it away, how long is it going to take to go through one cycle? What's the period going to be here? So now it's 4t instead of t. So how long will this one take with this different argument? So I'll give everyone a few moments to have some answer. And if you're not sure, let me know you're not sure. Then I know to say a little bit more. There's nothing wrong with being not sure. In fact, I'd rather know that you're not sure than just hear nothing. Okay, I got a decent chunk of responses there. So thank you to those of you who responded with something. Thank you to those who said you're not sure. I appreciate it. Just lets me know. So if it took going from 0 to t is equal to 2 pi before, notice here we have t and here we have t. Now with this other function, let's say x is equal to cosine of 4t. Now what we want to do is we want to see where this thing 4t, and actually let me just take this and color this. What's something I haven't used? Maybe I will use green. Okay, so there's some green there. And then here I'll also do green, but whatever. It's just so you kind of see the connection. So what you want to do is you want to see how long does it take for this argument to reach 2 pi? And quite simply, well, it's going to be pi over 2. So you just divide by the 4. One way to think of it is when you're multiplying by 4, you're in some sense going faster than you were before. If you think about it, the numbers you're plugging into cosine when you have 4t, they're going to be bigger than if you just plugged in t. So plugging in 4t for any given t values is going to be larger. So you're farther along, which means you've gone faster. Multiplying by this 4 speeds you up. And if you say, how long does it take t to reach 2 pi? Well, just 2 pi. How long does it take 4t to reach 2 pi? Well, t doesn't have to go as far because you're multiplying it by 4. So it's going to be pi over 2, or 1/4 of 2 pi. In the same way, with this example here, finding the quasi period, we look at the argument. So now if we go back to the argument here, and the argument's the same between sine and cosine, and combining sine and cosine you still get a sinusoidal curve. So you just have to look at the argument for one of them. You don't have to do anything fancy, given the fact that they're sine and cosine. You don't have to worry about all that. We're going to take the argument and we're just going to say, how long does it take 3/10 t to reach 2 pi radians? That would be a normal cycle, but because of this coefficient, it's either slowed up or slowed up, sped up or slowed down. And in this case, t will be, I guess, 20/3 pi. And when I say t there, what I might mean is capital T for the period. So this would be how long it takes to go through one cycle, where the cycle goes from a local peak to local peak. You won't reach the same level, but you're just going peak to peak. So this gives hopefully an idea how this works. And if you have questions, feel free to let me know in chat and I'll come back to this, but I will move on for the moment, but only because I'm not seeing any questions in chat. So what's the other thing I wanted to think about or mention? Let's see. Yeah, let's mention LRC circuits, or sometimes RLC. Someone asked about solving an LRC or RLC circuit, and I wanted to mention how it works. And just that it's really, if you're comfortable with spring mass systems, LRC or RLC is not going to be any different. So with an LRC circuit, or I call it LRC, you may see it as RLC because of the order in here as you go around. But it's essentially this. You have this circuit where in series you have a voltage that sends a current through here. So the current travels through a resistor. It goes through the resistor. Then it goes through an inductor. And then it goes through a capacitor. And then finally back. So you have this circuit here. There's three components: the resistor, the inductor, the capacitor. And you can form a model for the current, which we might say is I. So the current over time. We can form a model for this like so. We can say 1 over the capacitance times the current plus the resistance times the derivative with respect to time of the current. And then finally, the inductor times the second derivative with respect to time of the current. That's going to be equal to the derivative of E, the voltage over time, how much that changes. This is a model for an LRC or RLC circuit. When I use those phrases, I mean them interchangeably. I say LRC because of the order in which they appear. But some people might say RLC because you might see the resistor first before the inductor. What I mainly wanted to point out was, if here's the model for an LRC or RLC circuit that's in series, if you compare that to a spring mass system, like so, they have exactly the same structure. In the case of the LRC circuit, say with the second order term, you have an inductance, which has units of henries. That's different than having a mass in units of kilograms or grams or what have you. But it's still, once you just start analyzing it mathematically, it is just a constant number times a second derivative of a dependent variable. This is a constant number times a second derivative of a dependent variable. and so on. Constant times a first derivative, a constant times a first derivative, constant times a zeroth derivative, constant times a zeroth derivative, and then that's equal to just some function, potentially, could be zero. And then same thing here. So it's the exact same structure. So what are you going to do when you solve an LRC circuit that is just set up in this way? Well, you're going to find a characteristic polynomial. You're going to find the roots of that polynomial. And then every bit of analysis you would do on the spring mass system will be exactly the same in the sense that numerically, like it's no different. We are calling this dependent variable, we're calling it I, but there's really no difference between calling it I or X besides just kind of the nomenclature of it, like sort of how we've decided that we're usually going to call current I and we're usually going to call position X and so on. But in terms of the numerics and the mathematics doesn't really distinguish between that. It just sees a second order linear constant coefficient equation, and there's a process to deal with that. There's ways to analyze. The solutions are going to look the same. If you have a solution, you're going to, instead of looking at position, you're just going to be looking at current. So what's kind of interesting about that is that, oh, your current will in general oscillate, and there could be damping. So instead, if you have your current instead of your position, your current over time, you have, oh, it's oscillating and maybe dampening depending on the resistance or what have you. Now, someone asked, how do you know in what order to put the components? So the model will always have this, which is why I'm in the habit of calling it LRC circuit. So L will go with second order, R with first order, and C with zeroth order. As far as these here, I'm actually not very familiar with circuits. I'm sure many of you have already taken, will take, or are going to take at least one circuits class if you're in engineering or related things. So that'll be something you can ask in that class, or you'll see in that text. I'm not really sure offhand what the stipulations are for deriving the model from a diagram like this, from a circuit diagram. I don't know if you change the order of these, if it will change the model or not. I'm not familiar enough to say, but I would be interested. So if you find out and you want to tell me, that would be awesome. Okay, so I don't want to say really much more about this because the whole point was to highlight you're not really doing much different. In fact, you're doing nothing different in terms of actual computations and so on. How you assess what's going on physically, even then, you're just taking a different perspective, but the behavior is going to be very similar because you're still looking at a second order differential equation that has constant coefficients. So the way you go about finding the solutions are the same. The types of solutions you end up with are going to be the same. There's going to be damping or no damping. You could have underdamped and so on. I guess you might say, phrase it in terms of resistance instead of damping, but the principle is the same. So I just wanted to make that connection and really highlight that there is really not much of a change there from what we've been doing with spring mass. What I would like to do is to switch over to, oh, there's a helicopter. I wanted to switch over to the lab. I did not get to say as much as I wanted to about the improved Euler's method for higher order diffie-Qs. So I set something up and I want to show you this. So first, let me just double check. Can you all see an Excel type screen? It's actually LibreOffice, but can you see something like that? All right, someone says yes, that's good. So let me actually delete some of these columns so we can get everything in here. All right, good. Okay, what you should then see is a lot. What's going on here? And I can re-go through this from scratch, but I set this all up and I thought it might be easier just to kind of explain what I did. So I did this right before class. Remember last time, what we had was something like this. We had a differential equation here, which I think now might be a good time for annotation. We had a differential equation here. We had initial value information here. We use that initial value information along with the differential equation to compute these new values. And it was essentially an extension of the first order case, where before what we had in the first order case is an X column, a Y column, and then we had a Y prime column. And that would have been sort of you could think of this as the column that came from blue here and so on. We had 3 columns. So what changed is we somehow added another column. And you can think of it like you added this column that I just highlighted, or you can think of it like you added this column. But either way, you added another column from what we had before. That's just regular Euler's method. Euler's method just was a 3-column thing when you had a first order differential equation. When we scaled it up to second order, we added another column. If we had a third order differential equation, in chat, just to make sure I'm not talking crazy, guess how many columns regular Euler's method would require if you had a third order differential equation. So first we had 3, second we had 4. How many if we had a third order? Okay, yeah, good. Good. We would just add another column, but it would work in the same way where the last column would be sort of the computational column, and we would do the same types of computation. So this can be extended very naturally. In the same way with improved Euler's method, with the exception that at least the way it's laid out in the lab write-up, I find a little confusing. And maybe you've already processed it and it's fine and it seems super easy to you at this point. If so, that's great. To me, I found it a little, or have found it confusing in the past. So I wanted to point out this other way of setting it up. So going over to improved Euler's method, here's what's going on. For starters, we have the same second order differential equation. We have y double prime plus 3y prime plus 2y is equal to 0. That is over here. We have the same initial value information, that's here. We set up the initial value information saying we have an x value, we've got a y value, we've got a v value. Or said another way, we have a y prime value. From there, we can use the formula of y double prime, etc., to compute us a slope. Now, what I've described so far is exactly what we would have done with regular Euler's method in the case of second order. It's no different here. But you'll notice what I've done is above these 3 columns here. And you know what I really should do? I should even change this a little bit. Let me do this. I am actually going to add left to this, add right to this, I think this will make it nicer later when you have non-homogeneous. So let's call that x. And actually, x is going to be, yeah, this is, I think, a little nicer. Plus, this is going to be O 5 now. There we go. Okay. So if we look in these 4 columns, these are exactly the 4 columns that we had with the regular Euler's method in the case of second order. And what I just asked you was what would happen if we had a third order differential equation and we wanted to use Euler's method. Then we would have had 5 columns. Currently, I've called all these left. And when I say left, what I mean is that we're going to then also have a right, and then we're going to average the 2. So let's see how this works. From the left point x, what we're then going to do is compute a right point x. Now notice that is exactly the same as this one. But for a second, we're not really worried about this row 6 here. We're not worried about that. So we kind of ignore, oops, sorry about that. I grabbed the wrong area. We're going to ignore all this stuff for the moment. In fact, if we want, we can even just hide it. We sort of don't care about it. Let's hide that. Hide rows. Then what we're going to do is we're going to come up with all these right values, as it were. Now, why are we doing this? We want to have left and then right, and then we're going to take averages from there. We're going to use those averages to compute the new information. So all this stuff with the right, it's an intermediate step in order to get an average. The real computations, quote unquote, the real computations are going to come from using the averages. So the right is just a way to compare to the left and get an average. That's it. All right, so what's going on? Compute a new x value. We just added the step size, 0.1. Nothing fancy there. Now, how do we get a new y value? Well, the new y value is going to be equal to the old one, which is 1, plus the slope, which notice I've put it in this green here to show where it comes from, plus the slope times the step, or the step times the slope, either way. And notice if we take 0.1 times 0, that's going to give us 0. We add that to 1, and that gives us 1. So that's all that came about. In the exact same way, to get a new v value, what we will do is we'll take and say the v value here is equal to the last v value, which is 0, plus the step size times the v prime. So the v prime is the slope of v, so that's why we use v prime. And then that gives us, again, this negative 0.2 because it's negative 2 times 0.1. Finally, what we want is yet another v prime. So we simply take and compute this by using this formula. That's why I've highlighted in this sort of light blue. In order to get this negative 1.4, we use this information. So again, to get this negative 1.4, we're going to use this information here. That feeds into there. And I added this column with the x under the right because it could be, depending on what this formula is, it could involve an x, so that could require that you actually need the x. This formula doesn't because it's homogeneous, but it could be different. Now from there, what we do is we take an average. So how do we get it? This average, which is y prime or v, is simply v or y prime here, the left one. So now let me highlight the fact that we're using left. And then over here, we also take the v or y prime. And then again, let's point out that that is on the right. So there's a left one and there's a right one. And then from there, we take the average. So it's simply 0 plus negative 0.2, take the average. In the exact same way, if we want the v prime average, which is here, we say take the v prime on the left, take the v prime on the right, and then take the average. Here's what you get, negative 1.7. So all the right computations were just for the sake of setting up an average. Once you've done that, then we can compute a new y value using this slope. So computing this y value here, it's the last y value plus the slope times the step size, which gives us this. And then in the same way, if we want the new v value, it's equal to the last one, which is 0, plus the step size times the average here. And that gives us the new one. And at this point, this is all you need. If you want then to copy, you would go ahead and copy all these. Or actually, I don't need to copy out to the step, just here. You'd copy these. You'd say no fill there. And then you can just copy down. But I'm going to do one more without the fill. I'm going to copy this, and there you go. Then you have your set of x and y values. And if you want me to post this, just let me know, and I will get that up. But if no one wants it, then I won't. But otherwise, you all have a good day.